Okay, so hi, welcome back. We're gonna continue our discussion. So in the last video, we are talking about turbulence modeling. We're talking about tweaks to the DES model, and this is about delayed detached-eddy simulation. So this is DDES. This is one of the tweaks. Again, the paper is over here. I'll be pasting that in the link description below. So don't worry, this should be available for you to go and take a look if you want. So yeah, it should be available for free, so you can read out more detail on what I'm talking about. But this is just explaining the rough outline of why. This is explaining what the paper is talking about, the rough outline and why they developed the DDES. So in the last video, we were talking about two kinds of grids, right? So normally you want the what do you call that? You want your Reynolds average Navier-Stokes to switch on in the boundary layer. So if your boundary layer was, for example, this thick, you want to switch on the RANS model, the Reynolds average Navier-Stokes model, in the boundary layer. So you have to make sure this condition holds, right? So that your filter length is more than delta over CDES. So you have to make sure this is the case. You have to that your parallel length of the cells are very much bigger than delta, just to be safe. Your converse case is you want LES to switch on in the turbulent boundary layer of this you want LES to take over in the turbulent boundary layer. Then you do something like this, so that the RANS model, the Reynolds average Navier-Stokes model, would only switch on, I think, inside on the viscous sublayer. That's where you want it. Other than that, you probably want LES to take over. So this is what you do to force LES to switch on inside the turbulent boundary layer. Okay, so that's what you would probably do. Okay, because if you decrease your cell size enough, you should be able to get LES formulation. Now the problem comes if, let's say, you have your delta as such, and you were using the delta equals to max, max delta x, delta y, delta z. Alright, you are having delta equals to max delta x, delta y, delta z. That means the length of your cell in the x, y, and z direction, you just take the max length. If you have this delta, delta equals, if you have this this scenario, right? CDES times delta, or rather, how do we put this? Okay, you wanted this, right? Delta equals to, okay, all right. Yes, this delta over 20. So let me erase that. Okay, so remember, to switch LES on, you have this. You want to switch LES in all the turbulent boundary layer, you have this. Okay, and if you were to have this delta, for example, equals to delta over 2, for example. All right, so this is where you have the gray area. The gray area, or ambiguous region. Okay, delta maybe somewhere between you have delta be about 2, for example. Okay, it may not be that accurate, but what will happen here? Okay, what will happen here? That's the question we want to ask. So you have your grid spacing as such. So you have this this delta parallel equals to about half the boundary layer thickness. What would that happen? Okay, your scenario is this, that over here, or rather say over here, maybe in the first half of the boundary layer, or the first 2/3 of the boundary layer, you have your RANS formulation working out, which is fine. However, LES kind of kicks in a little bit early. So LES will kick in over here, within the boundary layer, within the boundary layer. And this is something you don't really want. It is not what DES is designed for. Okay? So knowing this is not what DES is designed for, you got to be very careful. You got to be very careful about how we space our grids. So for DES, we have to be careful about how we space our grids. Otherwise, LES kicks in too early, right? You have this simulation of the detached region a little bit too early, and that actually causes problems. What problem does it cause? Okay, so this early onset of LES causes problems. Okay, what's the problem here? Okay, so how do we put this in more simple terms? Okay, you have a situation here where, let's say over here we have okay, let's talk about the normal intention of DES first. Okay, let me find another grid for you. Okay, let's go here and go on this empty space. Let's talk about the original intent of DES, right? We have our attached region and free shear region. So I'll put your BL here, and I'll put your free shear here. Okay, so here the velocity is a lot higher in the free shear region, velocity high. You got lots of turbulence, right? Okay, in the boundary layer region, here you have less turbulence. That's to be expected. And how is turbulence being modeled in the boundary layer region? Over here, ideally you want Reynolds average Navier-Stokes to switch on. So you have turbulence modeled with μt, the turbulent viscosity. Now the thing is, as you transit from the boundary layer region to the free shear region, suddenly your viscosity here, your turbulent viscosity, is supposed to transit into actual eddies. Okay, because in the free shear region, in LES region, most of your turbulence, about ideally 80% of turbulence, okay, turbulence, ideally if you get your LES right, you have 80% resolved in eddies, and then 20% in the turbulence viscosity. So this is kind of an issue here. If, let's say, you transition from the Reynolds average Navier-Stokes scheme to the LES scheme, all right, from here to here, your turbulence viscosity drops, right? Turbulence viscosity drops. And what you need to compensate is this 80% of the eddies to kick in. Now that's a bit difficult. Yeah, now this is a little bit difficult if over here you don't have any eddies. Okay, you don't have any eddies here. And over here you have suddenly you need to artificially generate eddies in this transition region, right? Okay. The good thing about, I guess, the free shear region, that's one way of looking at it. That's how I like to think about it. In the free shear region, there are low wall effects. Okay, there are low wall effects. Yeah, so what you have is this case of turbulence viscosity dropping from the Reynolds average Navier-Stokes to the LES region, where you need to have this eddy generation to kind of compensate. Like I was saying, there were like low wall effects inside the free shear region. So it was more likely, well, this is the way I think, one way of looking at it, not the official way, but in the free shear region there are less wall effects, so that there are less impeding forces, there are less forces to stop those eddies from forming inside the free shear region, so that you have the correct amount of eddies being generated in the free shear region. So on the whole, the model should work, and this is what it was designed for. Now, what happens in the other case if we have this very ambiguous region where you have LES sort of activating prematurely within the boundary layer? What happens is then, okay, we will still have those eddies forming, but maybe it's not enough to compensate. It's not enough. Okay, LES activates, but not enough to compensate. Okay, compensate. Drop in UT. So this is what happens in this region, in this boundary layer region. Okay, why is that happening? Maybe this LES activates within the boundary layer where the viscous forces are stronger than the free shear region, and you don't have enough of those those eddies that's supposed to represent turbulence. Not enough of them form over here. Not enough eddies. Okay, not enough eddies form to reduce, form to compensate. Compensate, okay, UT loss. Okay, so that's what happens in this region. This there's a technical term for this phenomenon. Okay, let me shift this here, and let me copy and paste this. So this technical term is called model stress depletion. Why is it called model stress depletion? Remember the Reynolds stresses, the way we model the Reynolds stresses or the subgrid stresses is with the use of this viscosity. Now when we hop over from Reynolds average Navier-Stokes turbulence modeling into LES, we need to form enough eddies. All right, we need to form enough eddies, okay, to compensate for this drop in this eddy viscosity or subgrid viscosity. So yeah, that's called model stress depletion. And okay, so DES destroys model Reynolds stresses in LES, okay, i.e. nu T, okay. So LES transitions, okay, it has a LES transition without producing enough eddies in the LES region, for possibly because the boundary layer is still within the boundary layer and there's too much friction, too much shear stress forces, too much viscous forces within this region. So you need to stop LES from prematurely activating. Okay, we need to stop, or the proper term is called delay onset of, stop or delay onset of LES within the boundary layer. That's the idea of delayed detached-eddy simulation, or DDES. So how do we solve this problem? Okay, we take inspiration, or rather Spalart, the author of this paper, I think he is, let's see, yeah, Spalart. He takes inspiration from the K omega SST function. Remember in K omega SST, we had a very nice blending between two models as well. Okay, we have a very nice blending between two models as well, where the K epsilon was supposed to be inside the free shear region. The K epsilon model is supposed to take place inside this free shear region or detached region, and the K omega model is supposed to activate within the boundary layer region. So analogous to this is that we have the LES activating in the free shear region and the Spalart Allmaras Rens model, Reynolds average Navier-Stokes model, activating within the boundary layer region. Now the way this K omega SST model does the switch is with the use of some blending functions. So if you remember, okay, K omega SST uses a blending function, or several blending functions in fact, F1 and F2, if you can remember correctly. Okay, if not, you can go and see my previous videos on K omega SST. So yeah, they use these blending functions F1 and F2, and they were using some what do you call it, hyperbolic tangent functions. And well, there were some complicated functions, but the job was to switch from K omega inside the boundary layer to K epsilon in the free shear region. So what is the blending function of this SADDES? So yeah, Spalart Allmaras, or rather Spalart's idea was to take inspiration from this F1 and F2 blending function and make his own blending function for this DES model. Okay, Spalart. Okay, Spalart's idea was to take blending function to switch from Rens in boundary layer to LES in free shear. So this is what he did with the DDES. Okay, so this blending function is the key change from DES to DDES. Okay, what's the blending function look like? Okay, I'm not going to go through like step by step, but just roughly show what this blending function looks like. So this FD blending function is equivalent to 1 minus hyperbolic tangent of, okay, according to his paper, 8RD, and then you cube it. Okay, so this 8 and this 3 are constants. If you take a look at the original paper, the link will be in the description, or rather you take a look at OpenFOAM's documentation. Okay, if you see OpenFOAM's documentation on the Spalart Allmaras DDES model, okay, which is over here, they'll put this CD1 and CD2 here. So these are constants you can sort of calibrate. Okay, you can calibrate these functions, but in the original paper, these values are 8 and 3 here. It's very simple as that. And what is this RD? Okay, RD is equivalent to nu T plus nu. So this is the effective viscosity here. Effective viscosity over the square root, okay, or rather you have nabla into u. So this is the gradient of the velocity. All right, this is a gradient of velocity here. Okay, then you take the magnitude of it. What does it mean to do that? So remember, the gradient velocity is a vector. Okay, so this one we will have a square root, a dot product of delta u with, or rather, the gradient of u, nabla u, bullet, nabla. Yeah, we have nabla u times nabla u, which is the gradient dot product with itself. That will give you the norm I think the norm of the vector, which is basically the length. I mean, this is the L2 norm, I think, but basically it's just the length or the magnitude of this velocity gradient. Then you have two more things at the bottom. Okay, so you can see here it's a kappa square and y square. On the original paper we have kappa square and d square, right? So kappa square, okay, d square. So d square is the distance from the wall squared. That's all it is. And of course the fd will be put somewhere. All right. And the way we input fd is as follows, and I'll explain more next time. D tilde is equivalent to d, which is the distance from the wall, minus fd. So remember, this d tilde will happen in our Spalart Allmaras DES model. So you replace that d with this d tilde over here. Okay, so it's a max between 0 and d minus c DES delta. So this is the general form of the DDES model. Okay, this is the mathematical form. I'm not going to go into the derivation of it. Just keep in mind what its purpose and intent is. That's the main gist of this DDES model. Okay, so I'll stop for now. Thanks for watching. I'll see you guys next time. Bye bye.